So, good afternoon to all and welcome to lecture number 16. In this lecture, we will talk about the remaining features of texture and color. In earlier lecture, we talked about texture features based on the histogram, based on the edgeness, and based on the LBP, that is local binary pattern. So all those features we have seen how to calculate the LBP, how to extract the textural features from the histogram, and then how to extract the edgeness and so on. Now in this talk, okay, we'll talk about the remaining features based on the statistical approach as well as spectral approach, and also we'll see in short how to extract the color features. So this is today's agenda. First we'll start with co-occurrence matrices, how features of texture can be extracted by using co-occurrence matrices. So you know that a co-occurrence matrix is a 2D array, okay, that C, which is represented by C, in which both the rows and the columns represent the set of possible image values V. Okay, now you know that in the case of this one's color image, you have 3 planes, but in case of your grayscale image, you have only 1 plane, and the intensity value varies from 0 to 255. So V can be 0, varying from 0 to 255, right? So the value of Cij denotes how many times the value of I co-occurs, okay, means with respect to I and J, how many times it co-occurs with value J in some designated spatial relationship R, right? So this V can be the set of possible gray tones, like as I said that V is the, in case of gray level, this set of 0 to 255 gray levels in the image, and then we can establish the relation, like for example, okay, Cij relation, and based on that relation we can find out the co-occurrence matrix, how the value of I and J changes according to that relation. So let D is equal to dr and dc. So this is nothing but R means rows and C means column. So be a displacement vector. So D is the displacement vector. So where dr is the displacement in the row and dc is the displacement in the column. So D is the displacement vector. Okay, R is related with your row and C is related with your column, and dr is nothing but displacement in the row and dc is nothing but displacement in column. So and V be the gray set of gray level tones. Means, as I said, that this value will be varying from 0 to 255 in case of gray level. In case of your this one binary, it will be 0 and 1 and so on. So the gray level co-occurrence matrix CD for the image I is defined with this relation. So CD of Ij is nothing but the gray level co-occurrence matrix CD for what? For image I. And this is given by magnitude of basically R comma C and this I R comma C, which is equal to I and I R plus dr comma C plus dc equal to Z. So how those values are changing here, this will be more clear with the example how this relation, because this relation is decided by the user. Okay, in what way you would like to have the co-occurrence matrix and so on. So take the example here, like this is your original image I, having the values of intensity like as 0, 1, 1, 0 and so on. So here the intensity values are ranging from 0 to 2. So 0, 1 and 2 intensity values are there, and the size of the image is 4 by 4, means the rows are, number of rows are 4 and number of columns are also 4. Now see that the co-occurrence matrix C01 means basically your row is not changing but column is changing from 0 to okay, column is changing. So see this Ij, okay, what will be the this one? See that co-occurrence matrix. Now see that you are going in this direction, right? You are going in this direction. So in this direction, what is changing? It is only columns are changing, rows remain same na in this direction, right? And whereas if you go in this direction, okay, your row, this one column will remain same, whereas row will change. So this is first row, this is second row, whereas here this row will remain same, but column will be changed, this first column and second column. Now see, this is the value of z, right? Z is nothing but your column, and what is the value of z? That is 0, 1, 2. What is the value of row? 0, 1, and 2. So in this, basically here the value of row is 0 and value of column is also 0, right? So here we have to find the relation, like for example, what is basically this one, I and J combination, 0, 0 combination, how many times it is occurring in the original image, right? So see that this is the original image, and then I is 0, J is 0. So this combination, when you go from left to right, how many times this combination is occurring? Now see that this is the one combination, 0, 0, right? I is 0 and J is also 0, right? So if you put this one here, so you will get as a count 1, where I and J are having value 0, 0. Also here, this is I equal to 0 and J equal to also 0, means basically here. So okay, how many times you found the combination of 0, 0 in the entire image? This is 1 and this is another 1, so 2 times. So this value will come as a 2. Now this I is 0 and J is 1. So how many times this 0 to 1 is changing? So here you look that one, this is 0 to 1 is, so count will be 1 here. Again, what about this one? It will not come. What about this one? It will not come. What about this one? It will not come. But between this one also, it will not come. But this one will be 1. So count will increase by 1 when the value of I is 0 and okay, J is 1. So this combination you are getting 2 times. So this is 1 time and this is another time. So this value is coming as a 2, right? Now see that 0, 2 means I is 0 and here J is 2, right? I is 0 and J is 2. So 0, 2, how many times 0, 2 is coming? See that, is there any combination like, okay, when you put this one, okay, on any combination, are you getting the relation as 0, 2? No. So there is 0, 1 is there, 1, 1 is there, 1, 0 is there, 1, 0 is there, 0, 0 is there, 0, 1 is there, 2, 2 is there, 2, 1 is there, 1, 1 is there, 2, 2 is there, 2, 0 is there, 0, 0. But 0 to combination in original image I is not there. So that's why this count will be equal to 0, right? Now this one, okay, 1, 0, right? I equal to 1 and J equal to 0. So if you put I equal to 1 and J equal to 0, so like that way, how many combinations are there? So this is the only, this is one combination 1, 0 and this is another combination 1, 0. So these are the two combinations where you will find 1, 0 relation is there. Okay, 1, 0 and this 1, 0. So that's why this is 2, right? Then 1, 1, 1, 1, how many times? This time, okay, this 1 and this is another 1, so 2 times. Then 1, 2, 1, 2, where it is coming 1, 2? 1, 2 is not, okay, there is no relation between, as a 1, 2 relation between in the original image, so this is 0. Now 2, 0, 2, 0 is here 1 time, so it is 1. Okay, then 2, 1, so 2, 1 is 1 time here, so it is 1. Then 2, 2, so 2, 2 is occurring here 1 time and then here also 1 time, so it is 2. So in this way you got the co-occurrence matrix C0, 1, okay, with this relation, right? Now if you have the this one as a in a column direction, right? So what will be, like for example, 0, 0, if you go in a column direction, in a column scanning, 0, 0 is there? No, it's not there. So this value is there, this one. Now I is 0 and okay, I is 0 and J is 1 here. So I is 0, j is 1, 0, 1, one combination is there. Then other, no. Here also, no. But here you will find that 0, 1 is there. So, okay, and also here is you will find this one. So this is 3, right? I hope that you are getting what I'm saying. Are you getting?
Yes, sir.
Okay, fine. So this you got 3. Then 0, 2, right? 0, 2. So I is 0 and J is 2. So when you will get the 0, 2 combination, 0, 2 combination here, it is not there, but here is 1 is there. So 0, 2 is 1 here, right? Then 1, 0, I is 1, J is 0. You are going like this way, 1, 0. So this is one combination, this is another combination, this third combination, this fourth combination. So that's why it is 4, right? Then 1, 1. So I is 1, J is 1, 1, 1. 1, 1 is there. No, 0, 1 is there, 1, 2 is there, 2, 2 is there, but here also there is no 1, 1 combination. Yeah, here it is 1, 1 combination, so that's why it is 1, right? Then I is 1 and J is 2, so 1, 2. 1, 2 is here, one combination, and then no other place, so it will be 1. So similarly, I hope that you have got how to calculate the this co-occurrence matrix with this relation, Now this is the third co-occurrence matrix, C1, 1 means here, okay, in this direction you are going in this direction, so 0, 0, right? 0, 0 in this direction. Okay, I is 0, J is 0, one time. Then any other place? No, I don't think that the diagonal relation is 0, 0. So only 1 is there. 0, 1 in diagonal. 0, 1. This is 1. And is there any other? 0, 1. Yeah. So this is 1 and this is 1. So there are two combination of 0, 1 in diagonal relation. So that's why it is 2. Then 0, 2. Is there any combination of 0, 2? No. So there is no combination of 0, 2 in diagonal. So it is 0. Then 1, 0. 1, 0 is this one and then this one. Okay. So that's why 2. Then 1, 1. 1, 1 is here, right? So you got 1. Then 1, 2, 1, 2 is here. Okay, no rest of the place. So it is 1. Then 2, 0, 2, 0 you'll find here. So that's why 1. Then 2, 1, 2, 1 is not there at all here. So that's why it is 0. Then 2, 2, 2, 2 is there. Only one combination is there of 2, 2. So that's why it is 1. So in this way, you can find out the co-occurrence matrix. And then from that also, you can extract the features. And then that will be the unique features basically for textual images. And I hope that you have understood how to extract the co-occurrence matrix from the given relation. We can obtain basically this one features from this co-occurrence matrices. So two variation of the standard gray level co-occurrence matrix, like for example, here you get the normalized gray level co-occurrence matrix. Like how to get the normalized gray level co-occurrence matrix? NDIJ is the normalized gray level co-occurrence matrix, which is obtained from this CDIJ. CDIJ is nothing but your co-occurrence matrix, okay, with a given relation, and then summation over CDIJ. So that will give you the normalized. So for every this one, every value, you are just normalizing that one. So this is one way to obtain the features. Also, another way is symmetric gray level co-occurrence matrix like SDIJ. So symmetric here, SD IJ plus S minus DIJ. So this is called as the symmetric symmetric gray level co-occurrence matrix. So you can obtain the two variation of standard gray level co-occurrence matrix and so on. And then based on all those, whatever the matrix you get, from those matrix you can extract the features. So what kind of features you can extract? First one is basically, see that there are 5 types of features here I have shown you. One is energy or uniformity of that this one co-occurrence matrix. So summation over I, whatever you get the CD, so the CD is nothing but your co-occurrence matrix, and then this one summation over I and summation over Z and this n square D I comma Z. So basically this is nothing but your intensity, this one, Cochrane's value, and then you are squaring that one, and then just summation, doing the summation of that one. So that will give you the energy or uniformity. Entropy, you can also calculate the entropy of this one from the Cochrane's matrix, which is given by NdIj log to the base 2 NdIj. So this is minus sign because this otherwise it would have been 1 upon NdIj. Okay, since it is taken as a ND log to the base 2 NdIj, that's why this sign is minus sign. So this relation will give you the entropy of that Cochrane's matrix. So this can be one of the feature of textual feature which is extracted from the Cochrane's matrix. Energy can be extracted from the Cochrane's matrix, or contrast also can be extracted from the Cochrane's matrix, so which is given by I minus j square into NdIj. So this will give you the contrast. So this can be another third feature. And then fourth feature is homogeneity, which is given by summation over I summation over j of that Cochrane's matrix NdIj divided by 1 plus I minus j magnitude of I minus j. So that will give you the homogeneity. And then correlation, you can find out from the Cochrane's matrix, which is given by summation over I summation over j 1 minus mu I, where mu I and mu j are the mean, and this one sigma I and sigma j are the standard variation of rows and column sum, right? So column sum. So you can from that correlation you can find out the correlation as a feature. So from the Cochrane's matrix you can extract the energy feature, you can extract the entropy feature, you can extract the contrast feature, by you can extract the homogeneity and correlation. So these 5 features you can extract from the Cochrane's matrix, and that is directly on the spatial domain, right? So these are the features you can extract. Then another features you can also extract, like for example features based on Cochrane's matrix, like as a maximum probability. So what is the maximum value of NdIj? So that can be also used as one of the feature. So people can use either separate feature or in the combination of the features, and then that will increase the overall accuracy of recognition and so on. And then element difference moment of order k can be also calculated as summation over I summation over j I minus j raised to k into NdIj. So this will give you the element difference moment of order k, or inverse element difference moment of order k can be also calculated as summation over I summation over j NdIj divided by I minus j raised to k, where I is not equal to j. So that will give you the inverse element difference moment of order k. Also, this maximum probability gives an indication of the strongest response. So where you get the strongest response means where you will find the relation, like for example 0 1, if it is occurring several times, so that is giving the maximum probability, and that gives the indication that there is a strongest response of relation 0 1 or 1 0 or 0 2 2 2 and so on, the way we have studied. The second one has the relativity, this one. The second one has the relatively low value when the high values of n are near the main diagonal, basically. Okay, main diagonal. Then the third one has the opposite effect, basically here. So here, these 5 features you can extract, and okay, additional 3 more features can be also extracted from the Cochrane's matrices. And then what is the basically main problem with this Cochrane's matrices? Because see that one problem for Cochrane's matrices is how to choose the displacement vector D. So whether you should choose the displacement vector with the distance of 1 or 2, or whether you should go horizontally or vertically or diagonally. So basically, okay, that is nowhere this one clear-cut idea is mentioned. So it depends upon the user. Then statistical statistical test to select the value of D that have the most structure, that is to maximize the value. So you can okay, find the statistical test on the Cochrane's matrix by using this relation and so on. Right. The Cochrane's matrix features suffer from the number of difficulties. So which are the problems with this one? There is no well-established method of selecting the displacement vector because it is decided by the user, right? Then second problem of Cochrane's matrices is that Computing the co-occurrence matrices for different value of D is not feasible because a lot of computations are required there. Then third problem with the co-occurrence matrix is some sort of feature selection method must be used to select the most relevant one from large number of features, because we are extracting. See that I have shown you 8 features can be extracted. You can use, okay, you can also extract more features, but you don't know which feature is really giving the good result and so on. So feature selection method must be used to select the most relevant features, so that you can avoid the redundancy, and also you can reduce the dimensionality of the features, and then computation complexity will be reduced and so on. So after co-occurrence matrices, you have to use the feature selection matrix methods to select the good set of features. Otherwise, only number of features will increase, and that will increase the redundancy, or some kind of features may not be really useful, and then that will increase the dimension of the feature space and so on. So this co-occurrence matrices features are primarily used in texture classification tasks and not in segmentation tasks. So for classification of the textural images, these co-occurrence matrices based methods are used. Then second method today we are going to study, that is, see, after co-occurrence matrix, you can also extract the textural features in a spatial domain by using autocorrelation. So you know that you have studied the cross correlation, and then this one correlation, and then this autocorrelation in your DSP course also. So autocorrelation function of an image can be used to detect the repetitive patterns of texture element and fineness and coarseness of the texture. So how many repetitive patterns are there? That information will give you the autocorrelation this one function. So the autocorrelation function, say okay, rho d r dc of an n by n plus 1 by n plus 1 image for displacement drdc is given by, so this is the relation of autocorrelation, where r and c are basically the rows and columns, and dr is nothing but the displacement. Now you are considering, suppose for example, displacement of one unit, one row or one column, then this will be, this value will be 1, this value will be also 1, so r plus 1, c plus 1 and so on, and divided by summation of r equal to 0 to n. So n is basically number of basically element in that matrix, and c means basically number of rows are 0 to n, number of columns are from 0 to n. So I square r comma c, where I is nothing but the intensity of that pixel, and r and c is nothing but the location of row and column. So with this one you will get the autocorrelation value of that image. So if the texture is coarse, so from that how you can extract the features. So if the texture is coarse, then the autocorrelation function drops off slowly. See that this is the basically researchers have proved the relation that if texture is coarse texture, then the autocorrelation function drops off slowly. So these are basically the features which are extracted by using statistical approach, or particularly in a spatial domain itself. So in spatial domain, if I summarize, we have studied how to, okay, means basically finding the textural features by using histogram method, then local binary pattern method, and then edge directionness, then this one, autocorrelation, and then co-occurrence based matrices features. So these are the different ways which you can extract, by which we can extract the textural features in a spatial domain by using statistical approach. Now next one is, okay, you see here in spatial domain you are considering only the portion of the image, or small local portion of the image, and then you're extracting the features, then you are shifting to the right and extracting the features and so on. So this statistical features generally gives the important information about the local behavior of the image. But when you are considering the entire image, okay, so global behavior is given by the spectral approach. So in spectral approach, instead of considering the portion of the image, entire image is considered, and then transform is taken, and then you'll get the transform coefficient, and from that transform coefficient you can extract the features. So that is nothing but the spectral approach. Means what you are doing, what you have the original image, you are taking the transform of this image, maybe Fourier transform, maybe wavelet transform, maybe Gabor transform, or Laplacian or Gaussian, and so on. So like that way you can transform the image, so these original pixels will be converted into the coefficients, and then from this coefficient you are going to extract the features. Okay, so here you are not considering only part of the image, you are considering entire image. So that's why it is called the global approach. Okay, and then you are representing in a frequency domain, so that's why it is called as the spectral approach. So Fourier spectrum is ideally suited for describing the directionality of a periodic or almost periodic in 2D patterns. So the global texture patterns can be detected as a concentration of high energy plus in the spectrum, but quite difficult to be detected with a special method. So that's why basically global techniques are used. Now, spectral approach, there are three features of the Fourier spectrum. Means you can take the Fourier transform of the image, and then from that you can extract the features like as a prominent peaks in the spectrum, which gives the principal direction of the texture patterns, then the location of the peaks in the frequency plane that gives the fundamental spatial period of the pattern, and then third one is eliminating any periodic components via filtering, leaves the non-periodic image elements to be described by the statistical technique. So these three features you can obtain from the Fourier spectrum. Like, okay, so this is the Fourier, okay, this is the image, and then this is the Fourier spectrum of this original image. So that will give you the directionality as well as the magnitude. So detection and interpretation of the spectrum features, like for example, it expresses the spectrum in polar coordinates, SR into theta. So and then for each direction theta, S theta R is a 1D function, can be obtained, and for each frequency R, SR theta is 1D function. So a more global descriptor, you can calculate the SR and S theta. So SR is calculated as summation over theta equal to 0 to pi S theta R, and then S theta can be calculated from R equal to 0 to R0, so SR theta. So from these two, you can calculate the two features from the Fourier spectrum. This is your original image, and then this, okay, you get the Fourier spectrum of this image, and this from this Fourier spectrum you can calculate the two features like this way. Okay, radius is basically radius, and then this one angle. So in the polar coordinate R and theta coordinate, right? So this is basically spectral approach of the image. And then another spectral approach, like for example, you can obtain the steerable pyramid of the image, and then from that steerable pyramid you can extract the features. Also, suppose for example, I'll give another example, like, okay, if you are extracted the, okay, you can extract the textural features by using wavelet. So what you can do, this your original image is there, your original image is decomposed by using wavelet transform for one level. So after one level you get the four subbands: LL subband, LH subband, HL subband, and HS subband. Again, this LL in pyramidal structure, you can decompose the LL subband further, so you'll get four more subbands, that is LL2, LH2, HL2, and then this one. So this LL subband gives the approximate image, LH subband gives the horizontal direction, HL gives the vertical direction information, and HH gives the diagonal direction information. So from all those, see that if you have decomposed the image by using wavelet transform for 3 levels, so at every level you get the 4 subbands. So 4 subband for first level, 4 subband for second level, 4 subband for third level. So you get total 12 subband. Now on these 12 subband, I can measure the energy, like energy of first subband, energy of second subband. So E1 will be represented as energy of first subband, E2 will be represented as energy of second subband, E3 energy of third subband, E12 energy of 12 subbands. So I have extracted 12 features from 12 subbands. energy features. Similarly, I can extract the standard deviation of every subband. So how many standard deviation I'll get? There are 12 subbands, so 12 standard deviation. So I can use either energy features or only standard deviation or combination of energy and standard deviation. This whole image is represented now only with 12 or 24 features and so on. So we are considering the global approach here. So in that way also you can extract the textural feature by using wavelet transform. Similarly here I told you that steerable pyramid is there. But here pros are that it supports any number of orientation in steerable pyramid. So you can extract the directional information by changing the pyramidal direction. And then cons are is nothing. What are the cons of this one? Subbands are undecimated. So if subbands are undecimated, definitely the computation complexity will increase, memory requirement will increase. So you see that here you can obtain any directional information, frequency directional information with a steerable pyramid, but the problem is that computation complexity will increase. Then see that I told you that you can extract the features by using Fourier transform, you can extract the features by using wavelet transform, you can extract the feature by using Gabor wavelet, you can extract the feature by using complex wavelet, you can extract the features by using counterlet and ridgelet, edgelet, and so on. So there are several wavelets I have available, and you can extract the textural features by using any kind of transform. So that is nothing but the spectral approach. Here I have given you this one, a counterlet example, counterlet transform. Pros is that lower subband decimated is there. Cons are that number of orientation is a power of 2. So that is a con, and then from those we can extract the textural features. So as I told you that it's not only Fourier transform. You can use Fourier transform, you can use steerable pyramid, you can use Gabor wavelet, you can use standard wavelet, you can use cosine modulated wavelet, you can use M-band wavelet, complex wavelet, rotated wavelet, rotated complex wavelet, and so on. Counterlet and edgelet and ridgelet, and so many wavelets are available. You can use any wavelet for extracting the textural features by using the spectral approach. Okay, so here I have given you the Gabor wavelet. So Gabor wavelet will give you the directional information in different directions. So for example, if you have designed a 6 directional wavelet, Gabor wavelet, so you will get the 6 directional information in the texture. But problem is that Gabor transform is not a orthogonal transform, and then hence okay, it represents the image in overcomplete fashion, and then it requires more memory for storage. Computation complexity also increases. So these are the problem with this one. What is the advantage of this Gabor wavelet? Since the number of directions are increased, so definitely the accuracy of recognition will increase. So that's why you get the highest retrieval accuracy, or highest classification accuracy, or highest segmentation accuracy. And I think somewhere I have told you that Gabor wavelet, mathematical formulation of Gabor wavelet is very similar, or it is partially matching with our this one brain mathematical model and so on. So that's why this Gabor wavelet gives the more accuracy and so on. Then complex directional filter bank is also can be used. Complex directional filter bank for extracting the textural features in various direction of the texture. So pros are competitive, retrieval results are there like this Gabor wavelet, but here more computation complexity is there. So I told you that in summary, I'll tell you that you can use any kind of transform, whether it is a wavelet transform or a Fourier transform or a steerable pyramid or Gabor wavelet or complex wavelet or complex directional filter bank or ridgelet wavelet for extracting the textural features. So it is up to you, right? So this is okay. Standard database available of Gabor. This one. Texture, which is known as the Brodas texture database. There are 108 images are there. So from those texture images, you can create the database for doing the experiments. So 108 different textures, like as a bark texture is there, brick texture is there, bubbles texture is there, grass, leather, pigskin, raffia, sand, straw, water, wave, wood and wool. So see that this is the brick one, this is the bark one, and then straw, and then leather, and so on. So like that way, it is having some kind of texture. So this kind of okay. So these are the images which are used there in the which are there in the GRADAS texture database available. So this is the standard database of textual image, right? There's texture segmentation, like okay, this transform based method can be used also for segmenting the textural part based on textural properties and so on. So segmentation can be done based on color or texture or by using both, and you can use segmentation of natural scenes and so on, right? Now, the last features which I'm going to talk about today is the color feature. So, you know that color can be, there are color models like as a HSV color model is generally used by the human vision system. RGB color model is used for display purpose, and then CMY model is used for printing purpose, and YCRCB model is used for transmission purpose. You have a color model. From that color model, you can extract the this color features by using histogram or other this one. So conventional color histogram can be used either on a RGB model or CMY model or HSV model or CRCB. YCRCB model and so on. So you can extract the histogram of that one and extract the color features from those color models. So pros is that it is fast computation and simple color histogram methods. But what is the cons? High dimensionality. See that. So for example, if you simple take the RGB color histogram of RGB, see that you know that in R channel there are 0 to 255 gray levels are there, and then G channel again 0 to 255 there are there. B channel again 0 to 255 gray levels are there. So number of beams in the histogram of in RGB will be equal to 0 to 256 in R, 256 in G, and 256 in this one. RZ and B. So in total 768 number of beams will be there in the color histogram, conventional RGQ color histogram. So dimensionality will be very high, and then sometimes it may happen that no color similarity will be there, and then no special information will be there since you are extracting only the color information. Then fuzzy color histogram can be also used for extracting the color features. So advantage of that one is fast computation, color similarity is there, robust to quantization and noise, and this is also robust to contrast. But what are the cons of this particular histogram? So fuzzy methods are used here for that one. So high dimensionality is there, more competition is there, and then appropriate choice of membership weights are needed. So in HSV color model is used for fuzzy color histogram and so on. Then colorogram is also used as a feature, so which gives the spatial information, but problem with that one, it is very slow, dimensionality is very high, no color similarity is there, and HSV color space is there. Then color and shape method, that gives the spatial information, that gives the area, that gives the shape. And then cons with this one is that more competition, sensitive to clutter, and then choice of appropriate color quantization threshold needed, and then HSV color model are there. So see that color histogram, conventional color histogram can be used for extracting the color features, fuzzy color histogram can be used for color extracting the color features, or correlogram can be used for extracting the color features, or color and shape based methods can be used for extracting the color feature. So these are the different ways by which we can extract the color features. So to summarize this one, see that this is the correlate database of standard database which is available. These are the sample images of color image in the correlate database available. So this is all about the texture features and color features. So in texture features, we have seen how to extract the statistical features, how to extract the structural features, how to extract the this one spectral features, and then finally we have seen how to extract the color features by using 4 different methods. So this is all about color and texture features. in our next lecture, tomorrow's lecture, we will see how to extract the shape-based features. So in shape-based feature, again, we have contour-based features or area-based features and so on. So tomorrow we'll start the shape-based features. So we'll stop here. Thank you. Thank you very much.